For this last video on greedy algorithms, we'll be focusing on the minimum spanning tree problem. To explain this problem, we first need to define a few terms. First is that we can call an undirected graph connected if all of its vertices are in the same connected component. For example, this undirected graph is not connected because we have two separate connected components. But with just one more edge, we can make this graph connected. Then, if we have a connected graph, we can think about spanning trees of that graph. The idea of a spanning tree is that we're going to pick a subset of the edges so that the graph remains connected, but we don't have any cycles. And in undirected graphs, the term tree refers to exactly this case of a graph that is connected but has no cycles. So for example, in this graph, we could find a spanning tree by selecting just enough edges to connect all of the vertices. So if we take all of the vertices of our graph and select just the edges that I've highlighted in red, we now have a tree. And we call this a spanning tree of the original graph because we are able to connect all of the same vertices with a subset of the edges. In my definition, I specified that we are choosing a subset of the edges of size n-1. And when we combine that with the requirement for connectivity, it must be the case that none of the edges are wasted in terms of adding new vertices to the graph. You can check for yourself that the spanning tree in red contains exactly n-1 edges, and that it has no cycles, and that if we were to add any additional edge from the original graph, we would have a cycle. You can prove that this relationship between a connected graph having n-1 edges and having no cycles is true in general, but I won't go into that proof here. And now that we know what a spanning tree is, we can think about if this graph had edge weights, we could consider among the different possible spanning trees of the graph, which one has the lowest sum of weights. And this leads us to the minimum spanning tree problem, where we are given a weighted, undirected graph that is connected, and our goal is to find the spanning tree of the graph that has the minimum total weight. And at this point, an entirely reasonable question to ask would be, why do we care about minimum spanning trees? And as happens a lot with graph algorithms, minimum spanning trees come up in many different contexts. But one example we could use as motivation is the idea of constructing a grid for power or internet within a country. If we have a graph where the vertices represent different cities and the edges represent potential connections we could build between those cities, and our goal is to make sure that all of the cities are connected to our nationwide network, then if we find a spanning tree, that will be the fewest edges we could use to connect all of the cities. And if the weights on the edges represent the cost of those potential connections we might build, then the minimum spanning tree would be the cheapest way to ensure that all of the cities are connected to the grid. So now that we understand the minimum spanning tree problem, we could think about greedy algorithms for finding a minimum spanning tree. And already on the board behind me are 3 different greedy algorithms for this problem. All 3 of these fit our usual model of a greedy algorithm in that each one is processing the edges in some sorted order, and for each edge it's making a single decision of whether to include it in the spanning tree or not, and never looking back on those decisions. Among these 3 algorithms, we have 2 that are building a spanning tree from the bottom up, starting with an empty edge set and adding to it until we have a spanning tree. And the third begins with all of the edges in the graph and deletes edges until we are left with a spanning tree. Our first greedy algorithm, known as Prim's algorithm, starts by picking an arbitrary vertex in the graph and will expand out the spanning tree from there. Its while loop will iterate n-1 times to add each of the n-1 edges to the spanning tree, and on each iteration it picks the cheapest edge among the edges that would expand the tree that we have built so far. If our arbitrarily chosen initial vertex is this one, then on the first iteration we will consider all of the edges that have one end in our set so far and one end outside of it. So that would be these two edges from our initial vertex, and we will choose whichever one has the smallest weight, and then we will add that edge and the vertex on the other end of it to our tree. If we suppose the edge with the smaller weight was this one, then we will update W to also contain this vertex. So on the next iteration, we will consider all of the edges that connect a vertex in our set to a vertex outside of it, and so we will consider 1, 2, 3, 4, 5 different edges. And we will pick whichever one of them has the smallest weight and add the edge and its other end vertex to the set. So over the course of executing Prim's algorithm, we will gradually expand this connected subgraph that we are building by always adding the cheapest available edge that connects us to some new vertex. Kruskal's algorithm also operates by selecting the cheapest edges available to add. We instead will pick the cheapest edges no matter where they are in the graph, unless they would create a cycle in the graph we've built so far. So on the first iteration of Kruskal's algorithm, we will pick the minimum weight edge in the entire graph. Let's suppose it's this one. Then on the next iteration, we will go to the edge with the next smallest weight and add that. So it might be the case that as we add more edges, we might have totally disconnected subregions of the graph that we are building so far. We'll continue like this, adding in the cheapest edge, unless when we find the cheapest edge, adding that edge would create a cycle in the graph. So at this point, if the next cheapest edge were this one, we would skip it because adding it would create a cycle, which doesn't help us to build a minimum spanning tree. Over the course of this algorithm, we may have many subcomponents of the graph spring up when we add disparate edges, but over time, it should be the case that we will connect up those different components because all of the edges that are within a component will be rejected for causing a cycle. Finally, we have the reverse delete algorithm, which is, in a sense, the reverse direction of Kruskal's algorithm. In Kruskal's algorithm, we go through all of the edges from cheapest to most expensive, and we add an edge unless it would create a cycle. In reverse delete, we go through all of the edges in the graph in order from most expensive to cheapest, and we will delete them from the graph if that doesn't cause the graph to become disconnected. So if we look at the most expensive edge in the graph, and it's this one, deleting that edge will not disconnect the graph because we can still get between any pair of vertices. But if the next most expensive edge is this one, then we will not delete it because deleting it would separate our graph into two connected components. And so we would go on to the next iteration of our loop and find the next most expensive edge until we get down to just n-1 edges remaining. In class, we will discuss the running time of all three of these algorithms, and between now and then, I'd like for you to think about what data structures you could use to make these algorithms as efficient as possible. But for the remainder of this video, we're going to focus on proving correctness, and to prove correctness, we will rely on a lemma known as the cut property. The cut property says that if we cut the graph into two subsets, S and V minus S, the cheapest edge across the cut must be part of the minimum spanning tree. If I pick any subset of the vertices where my subset contains at least one vertex, and there's at least one vertex that's not in my subset, then we can think of that set as cutting the graph. We are separating the vertices into the ones that are in my subset and the ones that are not in it. And because the graph is connected, we know that this cut must go through some of the edges in the graph, because there must be some connection between the vertices inside and outside my set. So then the cut property asks us to consider all of the edges that cross the cut. And it says that among the edges that have one end inside my set and one end outside, we can pick the one with the smallest weight, and we know that no matter what cut I chose, the cheapest edge across the cut must be in the minimum spanning tree. And at this point, we are not committing to there being only one minimum spanning tree. We are saying that even if there were multiple minimum spanning trees of this graph, any of those MSTs must contain that cheapest edge across the cut. So I said that the cut property would help us prove the correctness of our algorithms, but first we need to prove the cut property. And the core idea is that if we didn't pick the minimum weight edge across the cut, we would have to pick some other edge across the cut instead, and that would increase the weight of our spanning tree. So towards contradiction, we are supposing that we have some edge that meets the qualifications of the cut property. That is, there is a set S where E is the minimum cost edge crossing the cut defined by S, and that the edge E is not present in our minimum spanning tree T. So to restate, our edge has one end in S, one end not in S, and it has the unique minimum weight among all of the edges that cross the cut. Now, because the edges in T span the graph, we know that there must be some edge in this set that crosses the cut. If there weren't, then we couldn't span the graph because we would have no way of connecting the vertices that are in the set S to the ones that are outside of it. So let's think about that other edge that's in T that crosses the cut and that has a higher weight than E because we know E was the unique minimum. So if T has some other edge that crosses the cut, and that edge has a higher weight, That means that we could take out that other edge and put in E in order to lower the cost of the tree. And if that's the case, we know that this spanning tree wasn't minimal. And I'll use the crossed swords to indicate contradiction, which means that our supposition was false. So now, if we're happy with our proof of the cut property, we can use the cut property to prove the correctness of our greedy algorithms. You should take a moment to make sure that you are happy with our proof of the cut property, because in fact you shouldn't be. What's missing from our proof so far is that we don't actually know that swapping in E instead of E prime will give us a spanning tree. It will definitely lower the weight of the set T, but it could easily be the case that if we took out one edge and replaced it with a different one, that we might have created a cycle over here and left something disconnected over here. Let's think a little bit more carefully about the case where this could go wrong. In this example, where we have the set S in blue and the rest of the graph V minus S in red, and this graph might have additional edges, but I've drawn here only the edges we're considering as part of our minimum spanning tree. If we consider the edges in black plus the pink edge E prime, then we have a spanning tree. There are exactly n-1 edges, all of the vertices are connected, and we have no cycles. But if we find out that the edge E in orange is the minimum cost edge across the cut, then we might like to replace E prime with E to lower the cost of our spanning tree. But if we did that, we would no longer have a spanning tree, because we would have disconnected this vertex, and at the same time, we've actually created a cycle. And so in this case, we can't actually swap in E for E prime. But hopefully this picture illustrates what we should do instead. Here, there's one other edge across the cut, and if E is really the minimum cost edge across the cut, what we could do instead is replace this edge. So it's not the case that we can just pick an arbitrary edge across the cut to replace. We need to be careful about which edge across the cut we pick, and we need to prove that there's always an edge that we can pick to swap for E and still have a spanning tree while lowering the cost. The key insight here to finding the right alternate edge is that when we added E, we actually created a cycle. Because we knew that T was a spanning tree to begin with, we know that there must be some way to get between the vertices U and V on either end of this edge. So we could find a path from U to V, and the first edge on that path that crosses the cut could be our E prime. So if we were to add E to the graph, that would create a cycle, and E prime was part of that cycle. So if we remove E prime, it will still be possible to go the other direction around that cycle to get between any of the vertices. And so that means that this replacement does still give us a spanning tree. So if we can now find an edge that we swap with E that still gives us a spanning tree and lowers the total weight, that would mean that T wasn't a minimum spanning tree. And so now we have achieved our contradiction, which shows that the minimum edge across the cut must be in any spanning tree. So now that we have a proof of the cut property, we should think about how to use this to prove the correctness of our algorithms. Well, if we think back to how Prim's algorithm operated, this was the one where we start with a single vertex and expand out, always maintaining a connected component. Then, with every step of the algorithm, we can prove that the vertex we choose must belong in the minimum spanning tree. Suppose that we started with this vertex, and then we gradually expanded out, adding this vertex, and then this one, and this one, so that now our set W from the Prim's pseudocode contains these vertices. At any time in the execution of Prim's algorithm, we are looking at the edges that cross from the component we have so far to the rest of the graph. And so our subset is the vertices that we've picked up to now, and we know that the cheapest edge from our subset to the rest of the graph must be in any minimum spanning tree, and that is exactly the edge that Prim's algorithm picks. So Prim's algorithm feels like it was built on the cut property, and our proof of the cut property directly gives us a proof of correctness for Prim's. For the other algorithms, we can still make use of the cut property, but we'll have to work a little bit harder. But I will leave those proofs as exercises for you that we can talk about more in class.